Thank you everyone for coming. My name is Alvaro Cea. I'm a research associate working with Professor Rafael Palacios. And the topic of today is geometrical nonlinear analysis of flexible aircraft on modern hardware architectures. As you'll say, thanks to Emily and Locke for the NVIDIA and Intel workshops as well. So let's start with a bit of motivation. So we have environmental goals. We have to combine this with economic viability and with an increased demand of people for travel. So we have these different concepts that are being proposed. One key concept is very slender wings to improve aerodynamic efficiency. We also have new aircraft configurations like this strut brace wing, this bubble, and also hydrogen aircraft. Now, this poses new challenges, and the ones we are going to focus on is aeroelastic couplings and geometric nonlinearities, which are critical for these new designs. So we have, on the typical analysis, it may need to be revised in things like maneuver loads, dynamic loads, also flight control, and for the design optimization, flattening instabilities. But here is a challenge, how we combine these nonlinear simulations with the demanding industrial requirements for design and certification. So very quickly, what is aeroelastic? Is the interaction between the fluid and the structure, and also, this is a bit more complicated, we have control and the inertial forces there. But what we have achieved is a framework for geometrical nonlinear elastic analysis. And these are some of the examples of these nonlinearities. So the aerodynamic forces follow the structure. This doesn't happen in a linear analysis. We have wind shortening, which is, you see the winds going up and getting shorter in span. We have also the CG, for example, it shifts, and also geometric stiffening. So the stress distribution changes, and that changes the way the winds react. So this framework is compatible with industrial models. As you have said, that this is a project led by Airbus. So we are working with their models, and we can do full FE Airbus type of models. But of course, what we want to do is to do this very fast. And now it runs in real time for some examples, or near real time. It's accelerated. It runs on modern architectures such as GPUs. And it also has a parallelization for multi-device cases. And the whole code is fully differentiated via ID. We just published this paper. Okay, so very quickly, the solution process, just to give you an overview. We start with a linear FE model. We condense it into the main load paths, where we apply the aerodynamics. We extract the linear modes. Now we compute this, we solve these nonlinear equations on the reduced model, and then we can compute the full 3D reconstruction of the displacement field, stress field, and so on. This will be the only equations that I'm showing. I don't want to scare you, but just very quickly, the important things are we have these nonlinear terms. These are cubic tensors, and they combine nicely. So they are formed after a Galerkin projection of the main equations and projecting the linear modes. We get these equations, which are not in the typical terms of displacements, but on velocities and stresses. And then we couple this with aerodynamics, and the forces come naturally as followers. So they follow the structure. Now, a bit of the algorithm and the data flow, it turned out to be really a code base that is very optimized. We had to look into this very closely, like the time complexity and the space complexity. So we start with our linear, stiffness, and mass matrices. We extract the modes. We call intrinsic modes. We compute the nonlinear couplings. Now we compute the system, so the modal coordinates, and we can extract the velocities in the structure, the stresses, the strains, and so on. Now, in terms of software and hardware, we are using JAX, which is a numerical library to enable high-performance machine learning, but we are leveraging on JAX for scientific computing. As I said, it's a very highly vectorized code base, has concurrent capabilities now. It can be deployed on CPUs and GPUs. And And in terms of the hardware, this is the HPC that we are using. So Intel CPUs and the NVIDIA GPU A100 running on the Imperial cluster. And I like this analogy between the CPU and the GPU. If we take the number of instructions as people that we can carry for very parallel tasks, the GPU is, as we are going to show, much faster, can do much more parallel tasks. Okay, so one brief note on automatic differentiation. For those of you who are not familiar with it, automatic differentiation is the art of computing derivatives of computer programs. So all the instructions are differentiable, and then using the chain rule, we can get derivatives of outputs from inputs. There are two modes: forward mode, it's very good for tall Jacobians, and the backward mode, so for a lot of inputs and only a few outputs. And this is the last part of the background. So we have parallelized this. This is a two-level parallelization for multiple load cases. So we can divide this onto as many GPUs as we have, and then even within the GPU, have these cases running in parallel. But okay, let's go to more interesting use cases. We are going to have structural and aeroelastic examples from canonical to full aircraft models, comparisons with commercial software, and CPUs versus GPUs, parallel load cases. So in this first example, this is a structural example. We are taking the wing from the tip. We are stretching it, and then at some point we will release it. And we are looking at the free vibration mechanics, basically, of this wing. It's very nonlinear. We see over 25% deformations. We have done differentiation on this one as well, but I'm not showing that. Now, an important point is, you see, with 50 modes, we can capture all the dynamics. And if you compare with the Nastran full FE commercial solution, that's 1 hour and 22 minutes versus the 10 seconds simulation of Pheniax. So that's one point. Now, we see a hype on machine learning models, but there are also physics-based reduced order models that we can achieve exceptional speeds without the train overhead or compromising accuracy. You see here the differences between the full FE and our solution, and that's the comparison as well. So yeah, that's a dynamic case. Now, this other case, this I call it the flying spaghetti. So this, we are taking the structure, we are putting, it's not moving. Let me see. Should have started moving. So this is a flying spaghetti. I don't know why it's not playing. But basically, we are throwing it into the air, and it starts flying. This is not clamp. Now this is, and it deforms a lot. So, no plane? Okay, well. Now the takeaway is when we run on GPUs, as we increase the number of modes we need, because in this example we can track the CG, so it's flying in the air, but we can track the CG and analytically. And when we compare it, we need a lot of modes to get a perfect convergence. And of course, you get these to scale those nonlinear cubic terms. If you have 300 modes, they scale, and then you have a large model base of computations. Now you can see here the GPU under 2 minutes, and on the CPU over 30 minutes. So here is where you start seeing the performance of the GPUs for these very large systems. On the next case, this is also a structural case, but here doing uncertainty quantification. So we have a stochastic field on the winds, and basically it's a normal distribution forcing terms. But then basically the key point here, if you do linear or very linear, you can extrapolate. You don't need, with one Monte Carlo simulation, you can extrapolate between the two. But once you go nonlinear, for every nonlinear case, you need to do basically as many Monte Carlo simulations as you need to converge. In this case, we were using over 1,600 Monte Carlo simulations. Each simulation takes around 17 seconds. So if you multiply, you get the numbers. Now, when we do this in the parallel CPUs, so using all the cores of the CPU, it gets on 300 seconds, but on the GPU you can see just over a minute. So this is very promising for sort of Monte Carlo analysis, where you need, especially if it's nonlinear, for each case that you want to analyze, you need thousands of simulations. If you want to do this with Nastran or other FE, then it will take hours times 1,000, and you see the computing power. Now, this is really what we do. This is aeroelastic simulations. Here, this is the XRF1. So this is an Airbus by Airbus. They have it for research. And so we are computing the trim, which is an algorithm. Basically, you need to find the balance of forces and moments with gravity and the lift and the angle of attack and the elevator to see how you can fly the straight, basically. And we are comparing against the Nastran, the linear solution. For small deformations, there is a very good match. And as you start increasing the G's, basically, you see all those effects that I mentioned before, the wind shortening, the follower forces, and this nonlinear aeroelastic trim runs under a minute. Okay, this one is not going to play there. Oh, yeah, the one plays. So that's basically the flight that you will see. You will never fly at 4G on a commercial aircraft. The maximum certification is 2.5 Gs, okay? But this is really to stretch the nonlinearities. Of course, in new concepts of aircraft, then you will see these kind of deformations at lower Gs. Okay, so that was a static aeroelastic case. Now, onto a dynamic case. These are gust responses. Okay, now you see this XRF1. This is over 1 million degrees of freedom. Is the kind of aircraft you will have for certification. So atmospheric turbulence, this is a cosine. This is an example of what you will be certifying when you see the bumps when you are flying. This is the kind of thing you need to look at the stresses of your wing. And here are the derivatives. So we are computing this in time domain, and we are also computing the derivatives with respect to the gas intensity, the gas length, and the flow density. And you see there is a very good match. So the whole computer program, the whole solution is been tracing all the computation and taking the derivatives of this nonlinear simulation. Okay. But now, okay, those are two gusts. Usually in the certification process, you have hundreds of gusts that you need to check because you don't know where is going to be the maximum. So here is where it comes the parallelization. So now this simulation for one of these gusts runs in around 27 seconds. So that's a very big system. As I'm mentioning here, is an ODE, the final system that you solve with 700 equations, 200 nonlinear equations. So it's running very fast, but now we want to run hundreds of these cases. So we do this on the parallelization. We are running 500 gas cases for varying the lengths, varying the airflow, and also varying the intensity. And here you can see the plots on the wind route, maximum stresses. Of course, the more intensity you put on the gas, the higher the stresses. But the one that is interesting is the gas length. So you can see for example, for bending of the wing, you have ones. For torsion of shear, you have others. And also for the minimum peaks, you have other points. And that's why you need all these different cases to be checked. Now, on the speeds, you can see on the CPU is around 27 times 500. And the CPU in parallel gets around 900 seconds. On the GPU, 38 seconds. For all these 500 cases, each of them is 700 ODEs. So you get over 300,000 of equations that are being marched in time. The final challenge that we have is now we want to take derivatives of this. So now you have hundreds of cases running in parallel, and you want to take derivatives of all these. It blows the memory, basically. Even the case before, it was over 60 gigas of memory. So now on this AD, it has 3 times more memory because it needs to track all the computations. So we came up with this, I call Forager pattern, because what we need to do is now we launch these hundreds of simulations, and now we gather whatever field of interest, for example, the stresses, and that gets to 10 to the 7, 10 to the 8 of size. And now we perform 2 reduction operations for example, over the hundreds of load cases and over time to get the maximum, to get the critical cases. And on those now, we launch AD. So we set up the AD and we launch again the program for the AD for those cases. So these are some examples of AD. On these two cases, as one of the critical cases around 75 and 110. And yeah, so the whole thing is working. And as a summary, so we have developed a framework for fast geometrical and nonlinear elastic simulations that run in parallel on modern hardware architectures. Plenty of examples, as you've seen, hundreds of cases that can be run in parallel on the GPUs. It's a differentiable parallel strategy for multiple load cases that you will have in a certification process. And all the cases, but the XRF one by Airbus are available open source. And yeah, with that, you have any questions?